Hi, pre-calculus students. We are going to talk about limits. So 712 and 713. Okay. So we're going to start out by thinking of two bugs on a graph. It seems silly. Okay, so I have two bugs on a graph, and when we talk about limits, what we're trying to figure out is what y values am I getting closer to as my x values get really big or really small or approach a particular number. So in the past, we've talked about end behavior and what happens as x approaches infinity or negative infinity. And we've written things like, as x approaches infinity, y approaches a number, right? Or as x approaches negative infinity, y approaches a number. So we're going to be talking about that and refining our notation a little bit, and then also talking about, well, what if x approaches a specific value? So in 14, it has us sketching this graph. And so when we sketch this graph, we should be thinking, oh, it's a parent function of 1 over x. That's a hyperbola that looks like this. This minus 2 moves it to the right 2, and this plus 3 moves it up 3. So these are like my new asymptotes. And then I can draw in my branches. I maybe, like how steep the branches are, it doesn't really, whoops, this should be getting closer to here. My pen's being kind of wonky right now. All right, so it says place your finger. I'm going to just use a highlighter to be my finger. You place my finger on the curve corresponding to x equals 5. So like around here, Benny the bug starts at this location and crawls along the curve, moving to the right. If he keeps moving to the right along the curve, what y value does Benny think he's approaching? So as he goes along and my x values are going this way, my y values are going down, 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 and they're getting closer and closer and closer to 3. So he thinks he's getting closer and closer to 3. Okay, so what we've just done is we have just found the limit of this function, f of x, as x got closer to infinity, as x got bigger and bigger, and it was equal to 3. So that is a way that we could represent what we just did here. Rather than writing out this sentence, this is called limit notation. So we read this as the limit of f of x as x approaches infinity is 3. And we have a horizontal asymptote. And we talked about this when we did end behavior. If you have a horizontal asymptote, then that is your end behavior. That's also the limit as you approach infinity. So that's another way that we can write this. Okay, so now moving on to number 15. It says use the graph at the right to answer the question. So here are our bugs, Benny and Bertha. Okay, so it says use the graph at the right to answer the questions below. Benny starts at a point on the curve corresponding to the point x equals 6. So x equals 6, so he starts like right here. Moves along the curve to the left, so he is climbing uphill. How high does Benny think he will get as x gets closer to 3? So as I climb, my x values are going to get closer to 3. The answer to the question here is, what are my y values getting closer to? What are these y values getting closer to? They're getting closer to 5. So as I approach 3 from the right, heading to the left, my limit is 5. Sometimes I think it's helpful if we're interested in what's happening at 3, to kind of just even draw like a little dotted line in here to help us. Okay, I want to know what happens to the y values as x gets closer to 3 from the right. And we would say it's getting closer to 5. Okay, the sister Bertha starts on a point at the curve corresponding to x equals negative 2, so like here, and moves to the right, moves this way. And we want to know how high does Bertha think she will get as x gets closer to 3. So x is getting closer to 3. These y values are going up, 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 but they're kind of leveling off here at 1. Okay, so as we're approaching from the right and from the left, instead of saying that, like as we approach 3 from the left, the y values get closer to whatever, what we're going to do is we're going to use limit notation. And sometimes it's called one-sided limit notation because we're looking at the limit from one side at a time. So as we're approaching from the left. Like here, how he was approaching from the left, but heading right. So when I say from the left, I mean on the left side of this X value of interest. So on the left side of 3. So we're heading to the right. The way we would denote that, so basically what we were doing right here in part B is I could say the limit of, let's say this is f of x, as x approaches 3, and we're going to say from the left, so we're going to put a little negative sign there, that means from the left, is 1. Okay, so in general, when we're heading from the left, it will be the limit of f of x as x approaches some constant, we're going to call it c, from the left. It's going to look like that. Okay, if we're approaching from, so this is like part B. If we're approaching from the right, heading to the left, like we did in part A, so from the right, heading left, the way we would write that is the limit, this is like what we did in part A, of f of x as x approaches 3, but from the right side, so with a little plus sign, is 5. And so in general, if this is any function, any c value, any constant, it would be as limit of f of x as x approaches c, and then from the right, we'll put a little plus sign, and then what does it equal? Because sometimes this notation is a little confusing to interpret at first. So you were going to see it a ton, but it's confusing because you see the minus and you want to think heading left, but it's that you start on the left side of the value, you actually are heading right. Okay, so let's take a look at 17. So this asks us to sketch this graph and then find these limits. So it's another transformation of 1 over x, and that's a shift of 4 to the right and down 1. Okay, this too would stretch it vertically, and probably the stretch doesn't matter so much when I'm finding limits. And if it just says a sketch, then this is fine. Okay, the limit here we want now of f of x is x approaches infinity. So as my x's get really, really big, I want to know what is happening to my y values. So I could start anywhere along here, and I just want to know as my x's get really big, my y values are just leveling off at this -1. Okay, and then this is asking for the limit of f of x as x approaches 4, which is right here from the left. So if I start to the left, this means start on the left side of 4. And people are like, well, where should I start? Like, doesn't matter if I start here, or if I start here, or if I start here. It really doesn't, because I want to know what happens as x gets closer and closer to 4. Is the result going to be different if you started here versus here? No, in the end, your y values just keep going down, 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 down. So we would say -infinity. Now, just so you know, your book would actually say that this limit does not exist because you technically can't equal infinity. And then it would say, but f of x approaches -infinity. It would say something like that. It doesn't exist, but the y values keep getting smaller, smaller, smaller. Okay, so I double checked with the calc teachers and they were like, this is actually preferred, but you should know what that means. Like when you see it, like if you took the AP Calc test, it might have this as a possible multiple choice answer. So like you should recognize what it means, but this is totally fine, just so you know when you're checking your homework answers. Okay, so now for this one, as I approach 4 from the right, so here's 4, I have to start somewhere on the right side of the graph. Again, doesn't matter where, because in the end, wherever I start, I'm interested in what happens when I get really close to 4, and these values just keep going up, 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 up. So we would say infinity. Again, your book would say something like, it does not exist. So I just wrote this and didn't say what it meant, right? DNE means does not exist. Like in Mean Girls, and she's like, the limit does not exist. That's what that means. Okay, so they would say DNE, but f of x approaches infinity. Okay, but just saying infinity is perfectly fine. Now, when we look at 18, it says an important use of limits is to describe the behavior of a function. Now, when we look at these limits in 17, what important feature is happening in the graph at each of these limits? So like here, when I was approaching infinity, I got closer, like an end behavior situation, I got closer to -1. Notice that in the graph, this is a horizontal asymptote. Now this is going to help us, recognizing this pattern here is going to help us when we get to these graphs in 18. All right, then when we look at these, as we approach 4 from the left and the right, it shot up to infinity and negative infinity. Notice there we have a vertical asymptote. So when you have, you know, an answer that's a vertical asymptote for your limit as you approach a value, that means you have a vertical asymptote at that value. Here, if you're approaching infinity or negative infinity and you approach a number, that's a horizontal asymptote. Okay, so in part A, it says, sketch the graph of a function so that the limit as you approach 1 from the left does not exist, but g of x approaches infinity. Okay, this is just another way of saying the limit of g of x as x approaches 1 from the left is infinity. It's kind of like going backwards from this, right? That's just how the book is going to write it. Now, for me, like I said, if I'm approaching 1, it just helps me, and it might not help you. It doesn't help you. You don't have to do it. But to like think about, all right, there's this vertical line at 1. That's what I'm getting close to. It says from the left. So starting somewhere over here. And as I get closer to the 1, my values have to shoot up towards infinity. It could be something like this, for example. If you wanted to say, oh, I'm going to have a branch over here too, I don't really need it for this. I just need to show that as I approach 1 from the left, I'm getting bigger and bigger and bigger. Okay, so this is sort of like, it's that I have a vertical asymptote here, like I had in this case. This says the limit as I approach negative infinity. So as I move to the left, my y values are leveling off at 2. Okay, when I'm approaching positive and negative infinity and I'm leveling off at a number, like I did here, that means I have a horizontal asymptote through 2. So just as I'm going to the left, right, lots of things could be going on around here, but as I go to the left, it has to level off. So I know it's got to level off at 2. And again, this could be doing all sorts of wonky things, or it could just kind of shoot up, or it could go like this. It doesn't matter. But as I go to the left, I have to level off at 2. So limits like what happens eventually, or what it gets really close to. All right, and then this last one, this one doesn't involve anything with infinity like this did. It says the limit as you approach 2 from the right. So here I'm going to sketch in a 2. It says it equals 5. This is actually sort of like what we saw over here. I'm approaching a number and it's telling me the number I'm approaching. Okay, so if they say the limit is 5, as I come at this 2 from the right, I have to be 5, or I could have an open circle at 5. I could just go like this. I could, and that could be it. I could also, it could keep going past it, right? The limit would still be 5. I could have, if I wanted, I could have an open circle, right? Even though it doesn't equal 5, it's still getting closer to 5. So that's an important thing to recognize too. And I don't know if anybody was wondering over here, like what was the difference when it's open versus closed in this one over here. It doesn't matter if it actually is equal to 5. It's asking, what are you getting closer to? Okay, so in this one here, I could say, if I had said to you, what is h of 2? Like, what is the y value when x is 2? You would say, well, you say that, it doesn't exist. But the limit is still 5. The y value is still getting closer to 5. Okay. All right, so moving on. So talking more about limits, these ones now come from section 713. So now we're going to refine our notation a little bit. So Benny and Bertha plan to meet their friend Sally Snail, and Sally is currently located as shown on the graph to the right. So here's Sally Snail. Benny starts at a point on the curve to the left of Sally. So here, and moves along the curve to the right. Where does he think he's going to end up? Well, he's going to end up with at the same location as Sally. All right, Bertha starts over here. She starts walking to the left, right? Where is she going to end up? She thinks she's going to end up at the same location as Sally. Unbeknownst to Benny and Bertha, Sally Snail has plans to get her shell shine today. Since she moved so slowly, she was actually already on her way to the appointment. She moved. How does this impact where Benny and Bertha each think they will end up? Well, even though this is an open circle and Sally's still not here, it's like what I was just talking about. If I were to put this on like a graph, right, and we say, oh, they're approaching where Sally Snail is here, they're approaching here. Benny and Bertha are still going to think that they're going to land in the same spot. So that being an open circle does not change anything, right? How does it impact? It doesn't, right? It stays the same. That says, does the limit exist for the situation in part C? That is, do Benny and Bertha predict they will arrive at the same location? Okay, so if a limit exists, so let's say we had this on a scale and this was 1. Here, I would say, you know, here the limit is 1, where we think Benny will land up, and here the limit is 1, okay? And if she moved, the limit is still 1. We're still going to the same place. So does the limit exist? Yeah, so we would say something like the limit of, let's say we call this f of x, as x approaches whatever Sally the snail is, so let's say S for Sally, I'll just even write it, is, let's say 1. So the idea here is if you're approaching this value from the left and the right, if they're the same, then we will say the limit exists, that it's possible to find it. If those values are different, we're going to say the limit does not exist. All right, so here's a bunch of practice. We've got a graph, and I would suggest that you practice them, like this is number 31, that you practice them on your own, and then, you know, kind of compare, check your answers, and then compare to kind of what I'm coming up with. All right, use a graph to complete each of the limit statements below. So the limit as we approach 2, or I'm sorry, -2, this first one is -2 from the right and then the left. And then when it says just the limit as x approaches -2, that means as you're coming at it, you're getting to the same y value from both directions, from the left and from the right. So as I approach 2 from the right, so that means I'm starting somewhere over here on the right, and I'm moving over this way, I'm moving closer and closer to this right here. What is this y? The question is, what is this y value? All right, and that y value right there is -1. Okay, now as I approach from the left, so I start somewhere to the left, doesn't matter if it's here or here or here, because I want to know what happens when I get really close to -2, and I look over here, and again, I'm getting closer and closer to -1. So since as I approach that -2 from the left and the right, since in both of them I get closer to -1, I would say the limit as I approach -2 is just -1. Okay. So now let's look at the next one. Now we are approaching 0 from the left and the right. Okay, so 0, that's just my y-axis here. Okay, so as I approach 0 from the right, so here's the right of 0, and people are like, well, what about this graph? I mean, sure, you can start there and go along, start on the right, move to the left, and then, but then it jumps down here and it goes down, 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 down. But in the end, it's getting closer to a y value of, is that -1 again, right? It's getting closer to there. Okay, now as I approach 0 from the left, so here, you might be, oh, there's a hole, whatever, you just jump over it, you just keep going, closer, closer to 0, still getting closer to a y value of -1. Again, these are the same, right? As you come in it from the left and the right, those are the same. So we would say the limit overall at 0 is -1. All right, now we're looking at this at +2. So looking here. Okay, what am I going to start with? As I approach from the right. So here's the right side of 2. Here I am going up, 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 and my y values are getting closer to that 6. And then I start over here on the left, and I go, I go, I go. I got to jump over that one, closer, closer, closer to, what is that? 3. So the limit of this is 3. Now, when you try to find the limit at 2, you're like, but wait, these are different. They're not the same thing. And for a limit to exist, is that you notice here, these are both the same. If these are different, then we say the limit does not exist, DNE. So what makes a limit exist versus not exist? So a limit as x, no, let's say this, a limit at x equals c, so some constant, exists when the left and the right hand limits are the same. So when the left and right hand limits are the same. Now, mathematicians do not like to write all these sentences, so what they do instead is they write it algebraically. So they say something like, if the limit of f of x as x approaches c from the left equals the limit of f of x as x approaches c from the right, if they're the same and they equal some number L, then the limit of f of x as x just approaches c is equal to that number L. Okay, so that would be like a formal way to describe if a limit exists. Okay, a limit does not exist if the left and right hand limits are different. So if the limit of f of x as x approaches c from the left is not equal to the limit of f of x as x approaches c from the right, then they don't equal each other. Okay, so we've talked about finding limits from graphs. Now how about from a table? Here it says write two one-sided limit statements that correspond to this function here. So if you have those a one-sided limit, then that means it's like the limit of f of x as x approaches some number from the left and the limit of f of x as x approaches some number from the right. Now, when I look at this table here and I look at values, like kind of what's in the middle, it's that on the left and the right, I'm getting closer and closer to 3. So this would be 3 from the left and the right. And I look at the y value. So from the left, like the numbers are smaller and getting bigger, the y values seem to be getting closer to 6.2. And then here, as the numbers get closer to 3 from the right, again, the y values seem to get closer to 6.2. So does this limit exist? Well, these are the same. So yes, because, right, the limit of f of x, or I'm sorry, I should have said h of x actually, approaches 3 from the left is equal to the limit of f of x as x approaches 3 from the right. And really these should all be h of x. Sorry, I didn't notice that until just now. Okay, and then it says, what is the value of h of 3? That means the y value when x equals 3. So I go to my table, my x is 3, and there is no y value. So I just say, I don't have enough information. I mean, kind of me thinking as I approach, it could be lots of things. It could be there's an asymptote. It could be that they just get closer to that 6.2 on either side. We really don't have enough information. Okay, and the last thing I want to just touch on is finding a limit from an equation. And so, you know, if you look at these and you're like, the first couple we did when we had an equation, it was something we knew the parent function for, and we could just graph the parent function, kind of figure things out. I look at these, I'm like, I don't really know what these all would look like. So we also need an algebraic way to figure out the limit. But what we're going to start with is we're going to look at the graph. Okay, we'll look at the graph for a couple of them here and then try to notice some things. I think I have them here. Okay. So I have all of those equations graphed. I also graphed just for myself because all of these are when they're approaching x equals 1. Notice, right? They're approaching x equals 1. I also then graphed the line x equals 1 and I made it dash just so I could kind of see a little bit better. And all these graphs are in Schoology in the chapter 7 folder if you wanted to pull this up so you don't have to type them all in. But as I look at this one, for example, if I want to know the limit, I would say, okay, well, what's happening as I approach from the left? Look at my y values. They're getting closer, 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 closer to 1.5. It says at 1, it's 1.5. And then on this side, look at what's happening to my y values, getting closer, 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 closer to 1.5. So I would say for this one that my limit is 1.5. Okay, then I could go to, I'm going to turn the next one on, turn this one off. Okay, and again, I could trace closer, 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 closer. See what's happening to my y values, bigger, 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 getting closer to 2. It seems up, but then it says it's undefined at 2, which makes sense because if you look at this equation, if you put 1 in the denominator for x, you would get 0 in the denominator. Okay, but on this side, same idea, closer, 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 and closer to 2. All right, so the limit for this one we would say is 2. And then I could go through and I could do that for all of them. I do want to just show you that algebraically what you could do, because for like, let's say this one right here, remember we had the point on the graph, it said 1, 1.5. What you could also do is just take this 1 and just substitute it in. 1 squared plus 2 times 1 over 1 plus 1, and that would be 1 plus 2, so that'd be 3 halves, well, that's 1.5. When I look at this one and I try it, I'm like, oh, I'm going to put 1 in for x. It's like, oh, wait, I get a 0 in the denominator. So what you would do is you would factor, like simplify what you can simplify. And look what happens. Those go away, and you're left with that's equivalent to x plus 1, which makes sense because our graph was a line with a hole in it, right? This, if I graphed x plus 1, would be a line. And if we were graphing this, we talked about this way back in like chapter 4 or something. Even the Desmos isn't going to show the hole, but there is a hole right there at that 1. So going back to this, if now I were to take this 1 and put it in here for x, 1 plus 1 is 2. Right? And that would work for all of these. Like some of them, like the simplifying might be a little bit more complicated. Like here, you would have to use a supergiant 1, but the idea is when you go through that, you ultimately would end up with something where you can put the number in with no fractions, and then you would be able to evaluate that limit algebraically. All right, let's look at F. All right, so I'm going to turn this one off. I'm going to turn this one on. Now, this is one where this one you would know the parent function for, or it's just a hyperbola. As I approach 1 from the right, okay, here, this one, if I approach from the right, it's going up, 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 it's approaching infinity. This one, as I approach from the left, down, 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 that's approaching negative infinity. So for this one, this would end up being does not exist. That's the only one in this set that would be does not exist. Okay, so like for example, this one, if I put 1 into this one, I'd have 1 plus 1 is 2, 2 squared is 4, I would get a 0 on the denominator. If I were to expand this, and then I get, what is this, plus 2x minus, whoops, this is a 4, sorry, minus 3. And then if I were to factor this, it would be x plus 3x minus 1. And then I simplify, and that would give me 1 over x plus 3. And then what I could do is I could put the 1 in here and here, and I have 1 over 1 plus 3, which would be 1/4. Okay, if I go back to my Desmos, and that was this one here, and then I trace and get closer and closer and closer and closer and closer. See what the y values are doing? They're getting closer to 0.25. And then if I come at it from this side, closer to 0.25. So for some of them, you are going to have to do some algebraic manipulation to make that work. Okay, like this one here, I don't know, I see that x, so I like a supergiant 1. This would be what, x squared minus x. Here, that would be 1 minus x. And then if I factor this out, I would have x times x minus 1. And this would be 1 minus x. These are super close. Do you remember the trick from last semester where if I want to flip this around, I can multiply the top and the bottom by -1. So I have negative x times x minus 1. And then this would be x minus 1. And then this equals negative x, and then I could put the 1 in here, and so the limit is -1. This one is tricky. I don't think I'd ever give you anything like this, but it's actually difference of squares. It's the square root of x minus 1 times the square root of x plus 1. Think about it. If you multiplied this out, you would end up with that, and then you have the square root of x minus 1 on the bottom, and it factors. I think that one's tricky. I don't think we would do that to you, but you're left with the square root of x plus 1. And then if you put that 1 in here, the square root of 1 plus 1 is 2. If you looked at the graph, it would get closer to 2 from both sides. Okay, hopefully that helps explain limits. Have a great day.